All right, well, we're a minute over the hour, so let's get started. Thank you everyone for joining what is the third webinar in the series of USV orientated talks. And this is a really a way of one of the mechanisms to generate really a community around USVs. And here we call this the community of practice for emerging USVs for the Global Ocean Observing System, for GOOS. And this has recently actually also been accepted as a UN decade project within OASIS. And for those that might be on this call for the first time or are not really totally aware of OASIS, OASIS is come out of a SCORE working group, which Megan and myself and Krista Marandino lead, and has a broad a community that ranges over several theme teams, which you could see more on the website, airseobs.org. And of course, we really welcome you to get involved if you are not. Masha's put the website address in the chat. Thank you very much. And if you click on Get Involved, you will be able to see how to register so that you receive notifications or join our efforts within the different theme teams, etc. So I please encourage you to do so. And today we're going to be having our third webinar in this USV series, which we're trying to have monthly. And let me go to the next slide. We are very fortunate to have three great speakers in this domain. Laurent Grare from Scripps is going to give us a presentation around wave glider observations and comparisons against FLIP. Marcel du Plessis from the University of Gothenburg in Sweden, he's going to be looking at storm ocean interactions and how they might impact fluxes, in particular in the Cape Basin area south of South Africa. And Dongxiao Zhang, looking at air sea fluxes in tropical cyclones and hurricanes from USVs, and I presume there's going to be sail drones in that one. That'll be about 30 minutes or so, or just under. We'll take a very brief question or two in between talks, so you're welcome to unmute yourself or raise a question quickly between talks. And then after that, we could have some more time, maybe about half an hour that's left, to have the panel, these speakers as the panel, to take more questions and to also take questions that might be more related to us as a community and the aspects we face as a community, whether it be around best practice and capability and how do the USVs form a part of the Global Ocean Observing System, whatever it might be. But there is a theme a bit today, and that is around the storms and the harsh conditions. So also think about how USVs really form an important part of observing difficult, rough conditions at sea, which we will hear a little bit more about today. And without further ado, Laurent, if you would like to share your slides so long, so I can introduce you. Let me see if I can just check you have that capability. And you are muted, just so you know.
Okay, so now I should be unmuted, and I'm gonna try to share. I lost the Zoom window.
No problem, take your time.
Okay.
So we also are always really looking for the next speakers of the future webinars in the next month and beyond that. So please put yourself forward and email Megan or myself or Masha or one of us in OASIS to say that you would love to give us a presentation of some of your work. It doesn't have to be long. We're looking for these 6, 7, 8 minute talks that prompt questions and prompt the discussions within the webinar. So it's not a big commitment, really. It's not a very long talk, and it's really just highlighting how you are using USVs in your science or monitoring around the world. So, Laurent, are you ready to take it away?
Yeah, so you see the full screen mode?
We do very well. Thank
Okay,
you.
all
Go
right.
ahead.
Okay, thank you, Sebastian. So, good morning, everybody. So, yeah, I'm Laurent Grare from Scripps Institution of Oceanography. So I'm just going to start quickly by introducing our lab, the RC Interaction Laboratory at Scripps in San Diego, California. So we are a small group, like 10 people-ish, 2 PIs, 3 engineers, and 4 students. So historically, we've been combining remote and in situ measurement from crew platforms, such as the MASS system, which is installed on a small plane. And also, like for the last 15, 20 years, we've been using FLIP quite a bit until it's been retired. And more recently, for the last 10 years, we've been working more with uncrewed platforms. So like the core of our research now is mostly with a waveglider. We currently have a fleet of 7 waveglider, 5 fully instrumented, and we just got 2 new ones that we still need to instrument. We got recently a Seawalker 5, which is the diesel unmanned vehicle and crew vehicle, like 5 meter long. And we also did some more UAV type measurement with the Sky Eagle or like the BG200. And yeah, all this work has been mostly possible through funding from ONR and also NSF and NASA. So, okay. So today I'm going to talk about characterization of the marine atmospheric boundary layer from an autonomous surface vehicle. And that's some work that I did with my colleague Luc Lena at Scripps and also Tom Farrer from Woodsole. So yeah, for the last 10 years, we've been using a lot of autonomous surface vehicle, waveguiders, sail drones, thin buoy to measure wind, temperature and humidity in the air to estimate ocean atmospheric fluxes. But since these platforms are still pretty new, we still wonder like how good are these measurements. And so in this study, we were fortunate to have measurement from waveglider aside from a FLIP, the stable platform near 10 meters. So we got this data set from the ONR-funded Lang-Marcel DRI experiment of Southern California, where we had flipped, moored, and 2 waveglider moving around. Do you see my my mouse?
Yes, we see it.
Okay, thank you.
Yes.
With yeah, waveglider roaming around with like a maximum separation with flip by 1 kilometer. And we had like a pretty wide range of condition with wind from up to 18 meters per second and significant wave height up to 4.5 meters. So for this study, we use anemometers and a weather station from FLIP mounted at 2 different heights, 14 meter and 8.3 meter, with a 3D anemometer from Gale to measure the wind and temperature humidity sensor from Campbell. On the waveglider, we have a bunch of instruments, but we only used the wind and temperature and humidity from the Vesela WXT weather station, which is about 1 meter above the surface. And we also use like the thermistor chain, which is along the umbilical to get the temperature of the ocean as close as possible to the surface. So first, I'm presenting wind speed, temperature, and specific humidity measured by each instrument at their own height, Z. So FLIP are like bluish colors and wavegliders are reddish colors. And we can see for the wind that for the highest wind, we have like some quite large difference, which is expected due to the difference of height measurement. For the temperature and the humidity, the difference is quite smaller, but we still observe some differences. One thing that I want to notice is that we have some instances where the difference are quite large, and it is due to waveglider capsizing. When the waves gets big, they just breaking wave just makes a waveglider capsize. So just a note saying that this data comes from the old SV2 model, which was a smaller one. And now the newer SV3 model are much bigger and more importantly, much heavier. And then they are more stable and less prone to capsize. So that's something which should be better with the new generation of waveguiders. So what we did, we extrapolated all the measurement at the traditional 10-meter height using the TOGA core 3.0, which is a bulk parameterization, which assumes the log profile for the atmospheric variable, such as, for example, this one for the wind, which is well known. So we see that using this parameterization, it does a really good job at extrapolating the wind at 10 meter. And for the temperature and humidity, it's kind of hard to see. So a better way to look at how this parameterization does a good job is to look at the XY presentation. So like in the X-axis, this is data from FLIP, and then the Y-axis, it is data from the waveguider that I combine. So wind, temperature, and humidity, and top one are data from at the height of the instrument, and bottom panel are at data at 10 meters. And so we can see that for the wind, it does a really, really good job. And for the temperature, we see that it reduced quite a bit the spreading and also on average reduce the difference. I'm going to go just quickly over that. So based on this parameter, U star, T star, Q star, we can compute the momentum flux, sensible heat flux, and latent heat flux. And we see that overall, it's also doing a pretty good job comparing data from FLIP and from the waveguiders with like a, for example, for the sensible heat flux and the latent heat flux, like an agreement within 10 to plus minus 10 watts per meter square, which was like the original goal from designed by TOGA core. So yeah, conclusion, the big takeaway message is that using autonomous surface vehicle measuring wind and atmospheric temperature and humidity at really close to the surface, we're able to extrapolate these values at 10 meter, and this extrapolation is really works well compared to measurements made really close to 10 meter. And so that shows that the waveguider, or at least the surface vehicle, are well suited to make such measurements. And yeah, as I mentioned, like new waveguiders are much more stable, and also like equipped with short and long wave radiometer, which should provide better and richer data sets. Thank you.
Fantastic. Thanks very much, Laurent. We'll take a quick question. I see Megan has her hand up. Do you want to ask a question quickly?
Quickly, that's just amazing to see that quality and the importance of doing the height adjustment for making that intercomparison. But what's remarkable is that the quality of the air temperature and humidity data seems to be good quality even after the submersion. Can you talk about that quality? You know.
Yeah, so something that I didn't mention. So obviously, like in this plot, I remove like the capsize event. But yeah, looking at like at the raw data, it takes one couple of minutes for the instrument to recover after a capsize. Like there you can see like the nice like extrapolation, like coming back to like the normal values. So it's I've been really cautioned by like trying to remove as much data as possible. So technically, like as soon as I see one capsize, I remove like a 30-minute average. So we could even like get more data from this data set. But yeah, it's I guess the one good thing is that like when it's windy, it's make it dry more quickly.
Yeah, that's great. Although windier means more sea spray, I suppose, if it gets too windy. But yeah, it's a tip.
But yeah. One thing though is that like we spend a lot of time. It took me few years and plenty of iteration before having the right waterproofing technique for this WXT. I fried a bunch. But yeah.
Thank you so much. That's great. We'll take some more questions for you at the end. So moving promptly on, Marcel, if you could share your screen. Marcel from University of Gothenburg, going to be showing us some small USV.
Do you see my screen?
We do. That looks good.
Okay.
Go ahead.
Thanks. So I'm going to talk a little bit about storm motion interactions and how we try and understand kind of the impacts of not only the atmospheric variability but also how these USVs can give us insight into how small changes in the ocean over small lateral scales are potentially important for fluxes as well. And so the work I present here is, of course, not mine alone. It's a part of this lovely research group here at the University of Gothenburg, which Seb is the lead of. A few researchers and PhDs involved in this work who have contributed to this exactly. And this is kind of an overview map showing some of our deployments. And the top right, you see South Africa and Antarctica, and you can see most of our work is in the Southern Ocean. Recently we've been doing quite a bit of work in the Cape Cauldron, which is kind of in this region over here, and that's what I'm going to be talking about now. But yeah, so one of the questions we're really interested in is, when you have these really rapid short scale bursts of strong atmospheric forcing, and here's just an animation from a reanalysis of showing the sort of storm structure in the southern hemisphere, you can see that making observations here is a very tricky thing to do. And so we feel that USVs can really give us the opportunity to do that, especially over longer time periods and in regions and places that we can't reach with ships, for example. And in that little box, I'm showing you kind of the region I'm going to be talking about, and this is a relatively new region for us that we're focusing on. And one of the reasons we care about this is this reason. So here I'm showing you the latent heat flux from a reanalysis. You can see these sort of rapid swaths of the storms passing through this area. But I think what's quite interesting is you can see with the ocean eddies, these cyclones and anticyclones that I'm showing as well, you can see the effects of the ocean on the atmosphere and these sort of longer lasting impacts of the mesoscale onto the atmosphere as well. But of course also this is a reanalysis, and this is not giving you the insight into scales smaller than the mesoscale. And so one of the questions we're asking is, well, what is the impact of those scales as well? And so one of the instruments we use is a sail drone, which I'm sure I'm just preaching to the choir here, but it's a really great instrument to measure air sea fluxes. It's relatively tall and robust, and the ones we used were kitted with the full instruments to measure the air
I'm sorry. Jessica, if you could mute yourself, or maybe we can mute her. Yeah, thank you.
And the little moving animation, what you see is the path that the sail drone took during our experiment. This was towards the end of last year, so August to November. And the idea here is that the sail drone measures across a various range of scales, from the subantarctic to the subtropics, through cyclones, anticyclones, and different ocean atmospheric conditions. And this is kind of a view into what we observed. And so we measured for about 3 months and covering over 4,000 kilometers during this particular experiment. But what you can see is a wide range of ocean atmospheric conditions that we sampled. So for example, if you look at the third panel, you see that we measured the wave height, and we can measure almost up to 8 meters of wave height, and so we're capturing really a nice range of intense ocean and atmospheric conditions. And so if I choose randomly some situations here where we have strong wave height conditions and strong wind speed conditions naturally as well, what we notice is that there is a response of the atmosphere to that, so certain atmospheric conditions, storm-like conditions, particularly with the air temperature and relative humidity. And so if we look at this in a slightly different way, we can identify the wind direction, because we know that in this area, the wind direction is associated with the storms is generally a south or southwest wind direction. We can see that there are sort of two different states occurring here. And the first, you can see where you have these high wind speeds and winds coming from the west, we have these warmer air masses, so warmer air temperatures and very humid air masses coming from the west. But also we have another state where you have winds coming from the south, and this is typically now from the Southern Ocean, and these are associated with cold and dry air. And so the trick is to now try and this is new work, and we're still digging into this, and so to try and understand what are the processes, the storm specific case studies and processes that are creating these strong contrasts in the flux properties. Another thing we can do is then start to dig into the reanalysis products and understand some of their errors. The wind speed and air pressure compared to the sail drone co-located measurements appear to be relatively good, we think. However, the radiative components, there is some large differences that we're seeing there. And so one of the next steps is to understand what are the conditions that are creating these differences, and do storm-like conditions have anything to do with this? The second platform we use is Sailboy, and so this is a relatively much cheaper and relatively robust instrument that we've used for many months at sea at a time, giving us really, really great data. And we recently deployed a Sailboy as a part of the Quiche experiment that Seb and others in our group were on just 1 or 2 months ago. And here we're testing out new capabilities from this with an extended mast to try and reach out a bit further away from the sea surface to get reliable air temperature and humidity measurements. And so here's a path or a trajectory of our Sailboy through this experiment. And it's a real challenge to pilot this thing, because it relies on the wind speed for its propulsion. And so the winds aren't always strong, and you're in a very turbulent area. So trying to get this to cross the strongest gradients perpendicularly can be a big challenge. But we managed to control it relatively well during this time period, and it's still out there as we speak, measuring parameters for us. But one thing that's quite interesting is what you see is, in particular, the section here where it sort of rides along the edge of the Gullis retroflexion. You see this really strong response in the relative humidity, which is the color shown by the dots. And so one interesting thing to think about is what is the impact of the ocean in this particular situation versus the atmosphere, which we saw previously as being a strong controller of the air-sea fluxes. It's been out for about a month now. Over 2,000 kilometers it's traveled, and like I said, it's still out there making its way to the northern parts of the Cape Cauldron. And this is the data that's sort of coming in. And just to note that there's a live feed of this. You can go to this website over here at the bottom to see the data as it's coming in, and from various other platforms as well in this region. Follow us on Twitter. We're also posting its updates there too if you're interested. But this relatively new sort of strategy, instrumentation that we've trying out in this experiment, these new relative humidity and temperature sensors and at different mast heights are appearing or seemingly giving us good data from the lower atmosphere, which we're happy about. And we did a quick validation against the ship-based sensors. And at least the first look, this hasn't been corrected for any height or anything like this, but the first look looks pretty good, and we're confident that we can get some really nice data out of this. Yeah, thank you very much.
Great, thank you so much, Marcel. Do we have any quick questions for Marcel before we get to our last talk?
I just have a quick question. Is there a sweet spot? What would be the ideal height above the sea surface to gather the most accurate data?
That's a very good question, I think. I don't have the, I mean, off the top of my head, I'm not sure I have the answer. Maybe there are others in this call who have a bit more experience about this. And that's kind of what we're trying to achieve here, especially trying to, you know, get in different atmospheric conditions, you know, with wave heights of, you know, 8+ meters. I imagine that in those conditions, it's obviously a lot more difficult with sea spray and everything else. So yeah, I'm not sure I have really the correct answer. Maybe Laurent from, you know, the previous talk can also shed some light into this. Just looking at those humidity measurements are great too. But that being said, we're measuring about 1 meter or so above the sea surface, and the initial measurements we're getting seem to be really, really good, at least compared to ship mast measurements.
Great, thanks. Maybe we can take that little part of the discussion afterwards about height and what are you measuring in the lower marine boundary layer. And so now we move on to our last talk by Dongxiao, who's going to be showing us some work on air sea fluxes in tropical cyclones. Do you want to share your, there we go.
All right.
Active coding at this time.
What do you see?
We see your terminal. There we go.
It's good? The full screen?
Yes, this looks very good. Go ahead.
Thanks. Okay, hi everyone. The title I'm giving now is the air sea surface fluxes in tropical cyclones measured by the cruise surface vehicle sail drones. Well, the surface turbulent heat flux fuels the hurricane intensification. That regulates the wind stress, also regulates the ocean mixing and stratification, which in turn would affect the heat flux. The drag of the wind also works to weaken the storm. Over the past 2 decades, hurricane track prediction has dramatically improved, while the improvement in hurricane intensity forecast has been rather limited. The lack of direct measurements at the air-sea interface inside the hurricane has long been recognized as the roadblock, since the rapid intensification depends more critically on the internal dynamics and thermodynamics of the storm. The safeties, like the one pictured here, prevent us from sending research vessels into the storm for measurement. We'd like to test if we can send USV sail drones to do the job. A more detailed analysis, including the relationship of direct covariance, momentum flux, and misaligned wave and wind, was presented in the recent AMS meeting, which I will not have time to cover today. Introducing the team. To rely on wind for propulsion and the solar to power the instrumentation and navigation control, the sail drones can sometimes only sail for about 50 or even 30 kilometers a day in the direction that we want them to go. But this mobility, even very limited, makes it possible to intercept and place this observing platform inside a fast-moving hurricane if planned well, which is the key here, planned well. The data collection and sail drone development for hurricane observation is therefore a large team effort. This team, co-led by Zhang and Greg Frost from PMEA and AOML, consists of both oceanographers and meteorologists, hurricane modelers and engineers, as well as scientists who fly on aircraft to deploy drop zones and underwater ocean glider operators for co-located measurements with the sail drones. During the hurricane season, we meet at least once a week to discuss the planned sail drone tracks and hurricane predictions, if any. Once the science objectives of the week are made, the mission managers will monitor and adjust the sail drone tracks in real time, adapting to the predicted hurricane conditions. Here, I'd like to highlight the earlier career scientists in this group. Some of them have served or will be serving as the mission managers of the upcoming hurricane season. The right figure shows the sensor packages of the sail drone for air-sea interaction observation. The hurricane sail drones were developed from the Generation 6 TPO sail drones with a shorter wing for stability to sustain the extreme weather and 6 days. The shorter wing will of course reduce the sailing speed quite a bit. The air-sea surface fluxes can be estimated with bulk algorithms using the measured mean state variables, often 10-minute or hourly means. The bulk algorithms that determine the transfer coefficients, such as the drag coefficient, here were derived from stability theories and direct covariance measurements, which are very limited due to the challenge in making high quality, high frequency measurements on moving platforms at sea. There has been lack of direct observations inside hurricanes in general. The sail drones are equipped with 2 GPS-aided IMUs, one in the wing, the one in the wing is for the motion correction of high frequency 3D wind measurements, therefore allowing for a direct covariance wind stress calculation. The one in the hull is for the ADC peak current measurements. The IMU data are also used to correct the downward solar radiation measurements and to derive the directional wave spectrum following something at all. In 2021, 5 sail drones were remotely piloted in 5 areas chosen for the high probability of experiencing the tropical storm winds. They intercepted 5 named tropical storms and 1 Category 4 Hurricane Sam. 3 sail drones coordinated with underwater gliders as shown by the pink tracks here and here to the left. The sail drone tracks are mostly blue, though they are colored here by measured hourly wind speed. The hurricane force winds were observed by the sail drone SD 1045 in the front right side of the SAM's eyewall. In 2022, 2 additional sail drones were deployed in the Gulf of Mexico. Although the number of storms were relatively low in the past season, 4 sail drones observed the different stages of Hurricane Fiana's development along the path. The trajectories of those sail drones shows they were mobilized to intercept the storm following the forecast tracks. Another sail drone east of Florida observed the re-intensification of Hurricane Ian after passing over the land. The left figure shows the sea surface salinity map and A-sky satellite winds on September 30th, 2021. The one-day track shows the sail drone was in the eyewall in the front right of the quadrant of the hurricane. Note that the hurricane passed over an area that is heavily influenced by the fresh water from Amazon and Orinoco River outflow. The 2 stars here were the locations of one Argo flow profiled 5 days before and after the hurricane, providing the background stratification of the ocean. In the right, the enthalpy of the total latent and sensible heat flux reached over 1,000 watt per meter square. The weak spike of downward solar radiation suggests that the sail drone may have briefly sailed out of the eye wall into the eye. Interestingly, while the air temperature dropped quickly by a few degrees, the SST increased even when the ocean heat release reached over 1,000 watt per meter square, which indicates the important role of the ocean process. It is further found that the drop of SST was coincident with the enhanced near inertial rotating currents that were forced by the rotating hurricane wind. We assume the Argo flow profile on September 25th provides the background information of the surface, the subsurface ocean before the hurricane. It shows the shallow temperature inversion at the base of the density mix layer at about 20-meter depth. The base of the temperature mix layer and top of thermocline was at 60 meter. So in between, there was this thick barrier layer. The presence of this barrier layer and the shallow mix layer means that SST should be reacting more strongly to the surface heat flux cooling, unless there was effective mixing in the ocean to bring the warmer water up. The ADCP currents show the velocity shear was just below 20 meter before 12 UTC, but at 50 meter or deeper beyond the ADCP depth range after strong near inertial currents were initiated. The shear instability or mixing develops when the Richards number is less than 1/4. This figure to the right shows the n squared times 4 in black, and the current velocity shear squared in red and blue for the 2 time periods before and after 12 UTC. The depth range where the Richards number less than 1/4 here during the first half of the hurricane pointed to the shallower temperature inversion, while during the second half, the blue arrow points to the top of the thermocline. So that's leading to a stronger cooling to the SST when mixing the strengthen. So in summary, the USV sail drones have successfully demonstrated their capability for hurricane observation in 2021 and 2022. The movie was captured by the camera on board sail drone SD-1045 inside the Category 4 Hurricane Zhang. For the 2023 hurricane season, we are in the process to deploy 10 sail drones, 7 of which will be deployed from St. Thomas, 2 will be in the upstream area domain A, 3 south of Bermuda, and 1 each to the north and south of Puerto Rico. 2 will be deployed from Charleston to the west and east of Gulf Stream. 1 will be deployed from St. Pete, Florida to the eastern Gulf of Mexico, with 1 reserved for rapid deployment in case of approaching hurricane before making landfall. That's it.
Wonderful, thank you so much. Big virtual round of applause to you and the others. I shall quickly share screen again. Right, before we get into questions, let me see, you're in the way here, all your faces. But
are there questions for Dongxiao?
Oh, sorry, yes, thank you. Any direct first questions for Dongxiao before we open it up? I can't see you now, so please just speak or someone else tell me.
That barrier layer that you saw was remarkable. That was 40 meters thick with an inversion for 40 meters. I mean, I've written many papers on barrier layers, but to see a temperature inversion that is that thick is, I think, really surprising, right? Or is it not so surprising in your mind? How long do you think that was lasting?
That's a good question. We look at this is only one AlgoFlow profile that we presented. We also look at other profiles that's available in that region. The barrier layer and the temperature inversion in that region is not uncommon. I guess the special area there is from the river outflow from Amazon and two bigger rivers there, and there are really with strong seasonal cycle. And on top of that, I think in that area, which normally have a strong, steady trade wind, which provide some kind of a cool effect in the surface layer, combine the two, it's pretty uncommon to find the temperature inversion and the thick barrier layer in that region. But it would be nice if we can measure. We can, in that situation, in that case, in 2021 during SAM, we were unable to direct the ocean glider away from the coast to the center of the storm. So we were not able to collect the co-located ocean profiles. It would be nice to have co-located measurements in the future.
Great, thank you. I think that's another major point, is how do we have co-located observations for the ocean interior too with these USVs, which is something to also figure out more as a community. Before I just thought, before we open it up, there are two things just to note on this slide. The first one is, of course, as I mentioned, please, we would like to hear from you if you would like to volunteer for future lightning talks in these seminar series. So please get hold of us, and we'll otherwise also come tapping on shoulders to prompt you to show your exciting work with USVs. And right now we're also in the throes of all the planning around Ocean Sciences meeting next year in New Orleans. And there are aspects around the USVs which we're hoping to profile and that are happening also within the OASIS community. Whether it's direct science sessions or hoping to have a side meeting, a short side meeting of about a day to get together as a community and progress some of the areas for USVs in a global ocean observing network. So please do volunteer and be in touch with us if you're interested. And we can talk, maybe if we have any more time in the last minutes, we could bring that up, or maybe Megan wants to share some more thoughts on that. Now this is just a prompting slide for questions and panel discussion. The yellow ones here are, while you've been talking, I've been thinking, what are some of the major issues that we kind of all face? Maybe not everyone in the high wind states, but some of these are really around the challenges that we're going to have observing, making USV observations in harsh ocean, high wind, big sea state conditions. How do we validate these? After Laurent showed us the work that they've been doing around FLIP, and then Marcel shows us, the Southern Ocean, where we have very little validation data against ships or otherwise, and the same for hurricanes. So how are we going to validate these very rough conditions? And what are we measuring with these USVs that are sampling at such low heights, 1 to 4 meters height or so, whether, which platform, depending on the platform you use. So what are we observing in the atmospheric boundary layer, and how does it matter to collect observations going forward at these heights above sea level? And then these white questions are ongoing questions that we need to ask ourselves within a community. What is our function as a community of practice? How do we understand that? What do we need to do to be seen as an emerged network, USV network? What are the attributes to get there? What other groups do we need to coordinate with, or that we can learn from as we become a USV network from other more established groups? Here, for example, Groom or the other glider networks or aerial drone networks that also are taking important measurements to understand fluxes, air-sea fluxes of various variables. So that's just to prompt you, but I will not share the screen. I will stop sharing so we can all see each other and take your questions for the panel and the rest of the community that's joined us today.
Marcel has his hand up, so.
Great. Well, Marcel, please kick it off.
Yeah. So I have a question for the other two speakers. Have you ever tried to measure rainfall from USVs? Do you think this is possible? And what do you think are the next steps that we need to do to achieve this?
So the WXT, they actually like measure the rain, which is, I don't know if you can say that it's like scientific grade type measurement, like it like kind of like just count the number of like a drop. But I haven't really looked at this data set, so I don't know how good and reliable they are.
Okay.
Yeah, at the earlier stage of the cell drone development, we thought about putting the rain gauges on the moving platform, but due to our experience on the buoys that we maintain in the tropical ocean and the North Pacific, so we decided not to do it because of the accuracies we worry about. But with that said, there are sensors, especially those acoustic sensor measuring rains, can be, potentially useful for the moving platform. Depends on the accuracy you are looking for. If you were just want to learn whether it's rain or not, I think still valuable to put on those sensors to try out. We also talked with different groups doing process studies, which is close to research vessels, and they actually said some encouraging things about those acoustic sensors for measuring wind. So I think there's potential over there. We need to explore further.
Mm-hmm. Yeah. Thanks.
Yeah, very good question. This is a big challenge. If you imagine, how do you measure rain with all the sea noise and wet stuff coming off the surface?
Last month, Oeki-san talked about measuring precipitable water vapor from the GPS, from the GNSS measurements from the wave glider. I think he's online, right? Maybe he could say something about those measurements? Maybe not.
Yeah. So we try to estimate precipitable water volume from the GPS, GNSS. So, but because of the interfere of the iridium transmission, we need many satellite information, but in the present status, only the GPS is effectable. The GLONASS data is not so good capture. Therefore, we can estimate the precipitable water volume in the very wider area, not a specific area. Therefore, we cannot consider about the smaller scale variability. That is a problem at this moment. But there is a potential.
Yeah, and precipitable water vapor is not rain, but it is a very valuable measurement for atmospheric dynamics. I have a question. Oh, well, actually, before
Yeah.
getting into that, I see Yolande has a question, so that's probably a follow-up.
Yeah, I just wanted to comment on the relationship between PWV and rain, and I think it could be useful. There's usually a very short period convergence around 4 hours when it rains, and you can see it as peaks, not spikes, but more just a slow increase and then drop of water vapor in the atmosphere when it rains. And and that's well published. So you could perhaps use it as a way to tease out, someone commented, maybe Laurent, about when you have like sea spray versus rain. So it might be useful if you had a rain gauge and you didn't necessarily trust it, that you could then look at the PW, if you had that as well, to look for that convergence. And then you could say, okay, that was a real rain event. So I think it would have value in determining whether something was rain or not.
Okay.
Great. That's very interesting. I hadn't thought about that approach to a validation in that sense. Megan, you had a question?
Yeah. Okay. So this is.
And if anyone else, please raise your hand so we can create a queue if you do have a question.
Okay. Getting back to the height correction and this remarkable agreement between the very low level measurements and the flip measurements at 10 and 15 meters height. Do you think that that works because the wave glider is a wave following platform, and so it's not like stuck in the trough of the waves and getting shielded by the waves, but it's actually kind of getting the highs and the lows, and it all averages out. I mean, if we had a moored buoy that was a low profiling, that, you know, would that be able to measure, you know, could we do the height adjustments on a low profile buoy, or is it, what's special is that it's, you know, a wave following platform, this kind of more free form? USV.
I mean, the wave glider and the buoy would be both wave flowing platform. So I don't see why you not be able to do that from a buoy.
Well, the moored buoy would have a big long line on it, so it kind of has a different dynamic and a wave response to the waves, but it might be.
Yeah, but the wave glider also has its own way to respond to wave action. So it would be different, but statistically, I don't see why the buoy or the wave glider would spend more time in the trough. There might be a slight difference, but I don't think it would be large. So
because I mean, for years, the conventional wisdom has been that that there's going to be shielding of winds in a wavy environment, and so a low profile platform will be underrepresented. The winds will be too biased low. But you're saying no, that's not how it works.
So we do see a slight undercorrection, like at the highest wind. We do see that the winds are slightly, like the extrapolated winds are slightly lower from the wave glider compared to flip. So there might be this effect a little bit, but it doesn't seem to be as large as what people thought about. And I do think like sheltering, it's also like a very intermittent process. So that's maybe why it doesn't happen every waves, and I guess that might explain why it doesn't have such an effect, a big effect. But I mean, yeah, I mean, it's still something to look at and to consider. And looking at the 3D sonic calorimeter, like doing some like phase average study and stuff like this, we might have a better answer about that.
Great. Dongxiao.
Yeah, one point I want to make about the different height of these sensors among different platforms. I think in addition to the intercomparison, just to verify the accuracy of different measurements, I think there's a real value also to looking to the processes, the different processes of these sensors in different height. So we know that if the sensor placed within the wave boundary layer, you're going to see the real physical process of those things that we still don't fully understand. I think Laurent, in your paper, showed the clear correlation between the wave height and your measured wind fluctuation. That's the real connection, the physical connection between the wave and the wind measurements. If you place your wind measurement above the wave boundary layer, you probably will not see that. For the hurricane measurements, we have a similar experience during high waves in those, although very limited, only a couple of hours of the 10 meter to 14 meter wave. We also see the anti-correlation between the wind measurements and the wave height on high frequency. That also tells us that there's a physical process going on. We shouldn't ignore about it. There's less study about those processes. And one hypothesis looking through numeric modeling, the LES models, the waves can also provide the pressure differences that can also modulate the wind. That's in addition to the shelting effect. Over.
Thank you. Jamie.
Yeah, thanks. And thanks for everyone for the great talks. I think this might be a quick question, maybe, mostly for Marcel, which is, if I'm remembering the slide correctly, you showed the ERA5 comparison with the sail drone winds. I think they were sail drone, not sail buoy. And they looked like almost a perfect one-to-one correspondence with the height correction. And with our sail drone data, my student, Sarah Nickford, who's on the call, found increasing bias in the ERA5 winds, low bias at high wind speeds. So like the ERA5 is not reproducing those high wind speeds. And we found like other papers that kind of support that result overall. And I was curious, was I not seeing it or did it not exist? Was the ERA5 essentially perfect there?
Yes, that's a good question. I'm just having a quick look because so you noticed that the sail drone was measuring stronger wind speeds when it was a higher wind speed. Yeah, so we see a small tendency towards that as well. We don't have a significant amount of data to show that yet, but yeah, to answer your question shortly, yeah, we do.
Thank you.
Yeah.
I'll just ask quickly, Laurent, those measurements, if I saw it correctly on the slide, was it true that they're all less than 4 meters per second wind speeds over that period, or no? I saw something with less than 4 meters per second.
It was like the difference, like at the highest wind, the difference between the measurement
I see.
at the wave glider height.
It was up to 16 meters per second.
Okay, great.
And the wave heights were up to 4.5 meters, right, Laurent?
Yeah.
Okay, no, that's great. I was just wondering what the ranges of your measurements, which would explain the capsizing and events, big, very stormy conditions. We are coming up on the hour, but Marcel, we could take maybe the last question from you before we start wrapping up.
Yeah, it's a quick one for the wave glider study. You mentioned that you had a thermistor string measuring the temperature. How close to the sea surface can you get? And
it's something like 30 centimeter, like even something like this. And we also had like a GPCTD on like a CTD on the skeg of the wave glider hull, but like it seems like on the thermistor chain, like the sensors stay more in the water, like while on the CTD on the spot, especially because of the capsize, like the measurements were cleaner from the thermistor chain.
Right.
Yeah, they give great profile, like because we have like 10 nodes, but the problem is that it slowed down the wave glider quite a bit. So there is a trade-off in between.
And does it impact its maneuverability, like how well you can steer it?
Yes, I mean, yeah, because as you get slower, it's getting harder to fight currents most of the time. Yeah, not most of the time, but yeah, I just wanted to say something about like the height of the measurements. I mean, for the wave glider, we are a little bit limited because we can't put like a 2-meter long mast. But I think like on a hazard platform, it would be really nice to have measurements at couple of heights or different heights, because it would give us more insight about what is the best height to measure humidity.
And it feels like, can we bring all our platforms to the same place and be there for a month, taking these measurements in some very variable atmospheric conditions or sea state, which would be something very nice to maybe talk about in the future as a community. How fun that would be. So we are a few minutes past the hour and all of us have to get on with our days. So thank you very much for joining today. It was great to see all of you and to have such a big presence at the webinar. And I remind you that the next one will be on the 22nd of June at the same time. And Mush has put there a link there to please register your interest to attend so you get the Zoom link. And that's where we'll leave it, and we'll continue these discussions with all of you at the next one and in between. And please do reach out to us if you're interested to be a speaker or also join some of the activities around planning for the Ocean Sciences meeting next year. All the best. Have a wonderful day.
Okay.